Okay, so let's start off with that problem that we mentioned at the end of class last time, which was the wire problem, right? So you have a length of wire, so have a length of wire, right? Let's say that the length is some number L, right? And you want to break it into two pieces. You want to break it into two pieces. You want to use the first piece to make a circle, so it's some length of fence, really. You want to use the first piece to make a circle, and you want to use the second piece to make a square. Right? And for some reason, you want to achieve the minimum area. Okay. So the question is, where should you cut the wire? Where should you cut the wire? Right? Should you cut it in the middle? Should you cut it one third over? Where should you cut the wire to get the minimum area? Okay. So take 2 minutes and see if you can set up. Yeah, Marcella.
So that one wire, you want to cut it and then use part for the circle and part for the square?
That's right. That's
okay.
right. So right, you could yeah. So you're going to cut it at some point, right? And then you're going to use this first part to you make the first part into a circle. You make the second part into a square, and you're hoping to. The contest is to make it so that the combined area is minimal. Okay. So the minimum combined area. Okay, there's a contest. Okay, talk to somebody nearby to say how you're thinking about it.
I mean, I guess. Yeah. I know. And then we'll get this in terms of like
As far as like relates to oh, because A is like a blend of
Okay, anybody want to say how they're setting things up? How are you setting things up? Anyone want to say? What are you calling the length of the first bit? Do you have any? Did anyone put any notation on it? No. So okay, so there's some number, right, and then there's L minus some number, right? See? I mean, you could have done it the opposite way. It doesn't matter, but you need to put names on. You need to put some variables in here, right? Because we're trying to use calculus on it. So you say, okay, let's call this first part x, right? So we're trying to figure out what x should be, right? How long should x be to minimize the area, right? Okay, if I call this thing x, then what's the area? Right? Area is going to change with x, right? What's going to be the area? I use the first part to make a circle, right? So I use the first part to make a circle. There it is, right? The perimeter, the circumference of this circle is x, right? And then I use the second part to make a square, right? And the perimeter of that is L minus x. So it's easy. Maybe let's ask this. What's the area of the second part first? What's the area of the second part?
the perimeter is L minus x, right?
The whole thing is, the whole length here is L minus x. So the length of one side is going to be
1/4.
1/4 of that,
L is
right? And so the area is
That squared.
that squared, right? Okay. Now what about this piece here? You know that the circumference is x, so what's the area? What's the area? Can somebody tell me? Or somebody figure it? Yeah, Kayla.
Hold on, I'm trying to figure it out.
Tell me how you're going to figure it out. You say, well,
Circumference is equal to like pi d.
pi d, right? 2 pi r is the circumference,
Yeah.
right? So what? So the radius is
Radius is
x over 2 pi, right? And so the area is
pi r squared,
pi r,
which is x over 2 pi squared.
right? So you get x squared over 4 pi squared, right? So x squared over 4 pi. Right? Okay. So depending on where we cut it, we get different areas. The areas are going to be, the total area is going to be this plus this. Okay. Okay. What do we do next? What do we do next, Nico?
Take the derivative.
Take the derivative, right? So, and then what do you do with the derivative?
Then we're going to do set it equal to 0 for the critical points.
Right, right.
I'm finding another one.
Right, exactly. Okay, so let's take the derivative, right? A prime is going to be, somebody want to tell me? When I differentiate this, what do I get? Nico, go ahead.
X over 2 pi.
X over 2 pi, right? I get 2x over 4 pi, right? That's x over 2 pi. Right? X over 2 pi plus the derivative of this thing. Oh, you can. And differentiate, what do you get when you differentiate that?
2
You'd use the chain rule, say, 2
L minus x over 4.
L minus x over 4 to the 1, right? Use the power rule on the outside function, right? Which is a power, of course. And then you differentiate the inside. What do you get?
L minus times L, or no.
What's the derivative of L minus x over 4?
1 minus.
Right? Derivative of L minus x over 4. L is a constant. L is a constant. The derivative of this. L over 4 is a constant, so when you differentiate it, 0. You differentiate this, you get negative a fourth, right? Negative a fourth. So times negative a fourth. Don't be confused by L. It's not a variable, right? It's an unknown, but it's a fixed unknown, right? It's not, the farmer's length of wire is not changing while you're playing this. Right? It's fixed. It's constant, right? Okay. So you get x over 2 pi, get negative. So I'm going to use the negative sign here to turn my L minus x into an x minus L, and then I get 16 on the bottom and 2 on the top. So I get 8. Right. So x over 2 pi plus x minus L over 8. Right. And putting it all together, right, you're going to get 8x plus 2 pi x minus 2 pi L over 16 pi. Okay. Okay, so you want to set this thing, you want to find where the zeros are. So just set the top equal to 0, and we divide it by 2. So 4x plus pi x minus pi L equals 0. I should have found a better common denominator. Nico, what is it?
What?
What's the question?
I was just thinking that if like you want the circle to be the smallest, so I think 0 is going to be a minimum.
You think that you're going to use the whole thing for the square,
Yeah.
right? Okay. We'll see. Right? Because you think, well, the square is sort of like a worse object than the circle, right? Because the circle, you think the circle is going to have the maximum. A circle is something that will contain maximal area in some sense. Your intuition is not exactly wrong. No, I mean that's a good way of thinking, right? The circle is certainly sort of like the optimal object for containing area, right? But it turns out that you're not quite right in this case. Okay, you'll see what happens. Okay. So what do you get? 4 plus pi x equals pi L. Okay. And so x is going to be pi L over 4 plus pi. Okay, so what do you see, right? You see that if this is 0 and this is L, then there's some point, in the middle, like around 4/7 of the way through, this pi over 4 plus pi L, where A prime is 0, right? Where A prime is 0, and you see that, from this positive slope here, that it's A prime is negative before and positive after, right? A prime is negative before and positive after. So what is this point here?
A local minimum.
It's a local minimum, right? Local min. And in fact, it's the global min because you know that it's the area is decreasing. You know that if you look at the area, it must be decreasing before and increasing after, right? So in fact, this is the global min, and it turns out that this is the right place to make your cut. Okay, pi over 4 plus pi times that's the right ratio to choose. Okay, any questions about that?
What does it have to do with, because you want like a, like this, does it also have to do with like the ratio of the side length to the area, so you want like two smaller shapes than one big square? Is that right?
That's right. That's right. So these two, what it's saying is that if you make, sort of, so it's saying that if you take, right, if you take this, what was it, pi over 4 plus, right, if you take this part for the circle and this part for the square, right, then those two guys are actually smaller than if you took the whole thing and made it into a square. Okay. Yeah, I don't have any sort of intuitive idea why that happens, but at least we can see that it does happen that way. Okay. Okay, so, oops. Okay, so any questions about that? Okay, so let's go on. So there's another sort of cool example that I would like to do, but I think we don't really have the time for it. If I find where it is in my old video, I will let you know. But it's the following question. You have it's sort of a classic optimization problem, which is the following. You have a can. Okay, you have a can. The radius is r. The height is h, and has a fixed volume. So can of fixed volume. Okay, and the question is, what dimensions minimize the material used, the amount of material used? Right, and this is an important question, right? You're trying to have a can, it contains, fixed number of ounces, right? And you're wondering, what's the best can? Right? Do I want to? If I take a long and thin can, does that minimize my area? If I take a really fat and short can, would that minimize the amount of aluminum I need to use? Okay. And you can answer this question using calculus. Yeah, Wynn?
Are you measuring the amount of material through surface area?
Surface area.
Okay.
Yeah. So amount of material, basically surface area. Surface area. But yeah, I think although it's kind of a cool question, I think let's go on to the next subject, unless people really want to see the can problem. Okay, close your eyes for a second. We're going to vote. Okay. Who wants to see the can problem? Who wants to go on? Okay, the can problem loses. Okay, which it probably should, I say. Yeah. But if I've done it in previous years, so maybe I can dig it up and send the link to you. Or you certainly can just do it yourself. Okay, so section 4.5, concavity. Okay, so here's the the rough idea. You have graphs that look like this. You have graphs that look like this, right? This is called concave up. This is called concave down. And you want to describe this. Right? Question is, how do we describe this mathematically? Right? How do we describe this behavior mathematically? Right? You don't want to say it goes up, it goes down. Right? That's not really math. Right? How do you describe this mathematically? Can somebody think of how this might be described? Raina?
So if you take the second derivative of a function, if that's, I think, if it's positive, then does that mean it's concave up, and if it's negative, that means it's concave down?
Okay, tell me why that describes this.
Because if you think about the second derivative as like acceleration,
Okay.
and if you think about it like on a graph, as the acceleration decreases, it's going to like the slope is going to like get smaller. So it would end up being concave down, and
Okay.
as acceleration increases,
Okay,
the slope
great.
is going to get bigger.
Great. So that you're thinking in terms of physics, right? There's something that happens to the velocity of this guy, right? The velocity, if you look at the velocity, right, the instantaneous velocity, looks like the velocity is pretty high at the beginning, but then it decreases, right? But the instantaneous velocity decreases, so f prime is decreasing, right? Well, if f prime is decreasing, you can think that, well, f double prime should be negative, right? F double prime negative, right? If this function is decreasing, if you're thinking in terms of the second derivative, that means that its derivative is negative, right? Its derivative is negative, right? Similarly here, the derivative of the derivative should be positive. Okay, so, right, so concavity, basically you think of as, so here's what the definition that we're going to use. If f is differentiable on AB, then we say f is concave up on AB if f prime is increasing on AB. Okay, and we say it's concave down if it's decreasing. Right, if you look at the picture here, right, you have this graph. F prime, the slopes are very negative here, but then they become less negative, less negative, less negative, less negative. The slopes are increasing. The slopes are increasing. We call this thing concave up, right? Right. This thing called concave up, we see that the slopes are increasing. This thing we call concave down, we see the slopes are decreasing. Right? Right? The slopes are decreasing. Okay? And so that's how we describe this thing using the derivative. Okay? Okay. And just as Raina said, there's a connection with the second derivative, right? If f is twice differentiable on AB, if f double prime is positive on AB, then f is concave up. Right? Right? Because because f double prime positive means that f prime is increasing by corollary to the mean value theorem. Right? Like the mean value theorem told us that if your derivative is positive, then u must be increasing. Okay. And similarly, of course, if f double prime is negative, then it's going to be concave down. Okay, so some simple examples, right? Is trivial example to start off with f of x is x cubed, right? You take the first derivative, you get 3x squared. You take the second derivative, you get 6x. You get 6x. So, right, that's the second derivative is 0 at 0, right? And it's negative before and it's positive after. Right? So that tells you that f is concave down here and concave up here. Okay. Just like before, don't get mixed up between your function and your derivatives, right? This is the second derivative. The second derivative is negative here. It's positive here. Right, that's not saying anything about the values of f. Okay, it's just telling you that f is concave down and f is concave up here. Okay. In this function, our function actually is negative here and positive there, but that's just a coincidence. So you know probably what x cubed looks like. Right, x cubed looks something like this, and indeed you see that it's concave down here, right? The derivatives are decreasing, right? The derivatives are decreasing, and then the derivatives are increasing. Okay. Okay. Let me ask you to do one simple problem along the same lines. So f of x is 2x cubed minus 3x squared plus 12x plus 1. Take a minute and figure out where it's concave up and concave down.
Is that plus 12x or minus?
Plus. Oh wait, should have been minus. Sorry. It'll probably work out better if it's a minus, so keep it as a minus. turn to somebody nearby and talk with them, please.
Oh, you're saying. What happened?
Where it's positive typically, you just plug in.
Oh, it's plug in.
Yeah, plug in say
One.
zero.
Oh, zero. I'll plug in 12 minus 6. That's fine. Right at 1/2.
Okay, who would like to say what? Kayla, go ahead.
And then 0.
So f prime is what?
6x squared minus 6x minus 12.
Mm-hmm. Double prime.
Is 12x minus 6.
Okay,
X
yeah.
equals 1/2.
So x equals 1/2.
0 at 1/2. And then I plugged in 0 and 1.
Mhm.
And I got negative.
Negative and positive, right? You don't even have to plug it in because you can see that this is a linear function with a positive slope, right? The slope is 12, so you know it's going to be, if it's 0 here, it must be negative before and positive after, right? It's a line, okay? And so that gives it to you, right? This is concave down. So f is concave down here and concave up. Okay. So there, just as in the previous one, there's this point where the concavity switches from one to the other. That kind of point is called these sorts of points are called points of inflection. Where the concavity switches sign. Okay. 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 So concavity has a really nice. The second derivative has a really nice application to classification. The classification of extrema. There's a theorem that says the following: if f is twice differentiable on AB, and you have a critical point in there. If suppose you know that the second derivative is positive, the second derivative is positive at that same point. The second derivative is positive at that point. And actually, to be perfectly honest, this should be something called twice continuously differentiable, which means that the second derivative exists. Derivatives are continuous. Sorry. You don't really need to worry about that, but it just bugs me that I'm not being completely honest unless I write this down. Okay. I want you to think for 1 minute about what this is going to say. If the second derivative is positive there, okay, so you have a critical point and you know that the second derivative is positive there. Think about what that'll tell you about whether or not this is an extrema. Right? Try to think, just reason it out. What's going to happen? Okay, talk to somebody nearby. See if you can make your argument. What's going to happen?
Tell you what the next one. I think we can tell you
Because I think it was this way. See, first derivative is 0.
Look, it takes money.
Like different.
And then it's concave. It's going to be this way. So that's the derivative.
But it's kind of that one. First it tells you whether or not it's like where they tell you where it changes, it doesn't tell you about it, and it's going to tell you if it's going up or down. It can tell you if it's a little different. I'm interested in seeing it.
Okay, who can talk it? Who can talk it through? Who would like to give some reasoning for it? Go ahead, Wynn.
So it's going to be a local min at the least because when the derivative is 0, that we know that's an extrema.
It's a possible extrema.
A possible
Okay,
extrema. And if the second derivative is concave up, then it's going to be going like this.
If the second derivative is positive, then it's
Yeah.
going to be concave up. Okay. So yeah, so you say, well, look, here is c, right? And you know that the function, the derivative is the tangent line is flat there, right? The tangent line to the graph of f is flat there, right? You also know that the second derivative is positive there, right? And what that tells you is actually that the second derivative is going to be positive nearby. Okay, this is the part where the continuity is needed. Okay, so really, the second derivative being positive there gives you that the second derivative is positive around, so near c. Okay, and that's the part that's sort of concealed in this argument. Okay, but that means that your function is concave up, right? You're going to be concave up, and so it's going to be a min. Okay, that's one way of thinking about it. Another, pretty similar way of thinking is to say, well, look, the first derivative is 0 there, right? So if I'm looking at the first derivative, and here's c, the first derivative is 0 there, and the second derivative is positive, right? So that means that before it's smaller, right? Before it's smaller, and after it's bigger, right? Because the second derivative is positive there, so it must have been negative before and positive after. So in other words, the f prime is negative before, right, and positive after, right? Negative before and positive after, and so it must be a min. Okay, I actually like the second way of reasoning a little bit better. It's more tactile somehow, right? And you know that the derivative is 0 here. You know that the second derivative is positive. So the first derivative must have been negative before and positive after. Negative before and positive after means that it's a min. Okay. Any questions about that? Yeah, Isaac.
If we have a number of them, then can we figure out whether or not it's a global? Like, can we use this to figure out if it's a global maximum?
Well, this will only tell you if it's a local one, right? This will only tell you if it's a local one, and you probably, it sort of depends on the problem, but if you were on a bounded interval, right? Then you'd play the game as before. You'd say, well, I'm going to look at my guys and see which one is the biggest one, right? So this test doesn't tell you at all if this is a global min or not. It only tells you that it's local. Okay. So you get a bunch of local. You get your critical points and endpoints. You would classify them, and then you would evaluate them to see which one is the biggest to find which is the global max and global min. Okay. Other questions? Okay. So okay. So of course you have this other thing, right? If then it's a local max, right? Exactly analogous arguments, and if it's equal to 0, then you don't know anything. So no, that doesn't tell you anything. Could be, you don't know anything. Okay, so yeah, let's look at this one. We did this. So let's go back to an example that we considered, a few times now. F of x is x cubed plus 3x squared minus 45x plus 2. We already have seen this one more than once. In fact, this was on your exam. So f prime is, of course, 3x squared plus 6x minus 45, which is the same as 3 times x squared plus 2x minus 15, right? Which is the same as 3x plus 5, x minus 3. Right? So we see for this guy that f prime is 0 at negative 5 and at 3. Right. And the last time, right, we figured out what these things were by using the first derivative test. Right? We said, well, look, it's positive here, negative here, and positive here. Right? The derivative is positive, negative, positive, and so this must be a min. And this must be positive, negative, negative, positive. Oops. This must be a max, and this must be a min. Okay. So that was using the first derivative test. If we look at the second derivative is going to be 6x plus 6. Right? And we see that right, f double prime at negative 5 is negative 24. Double prime at 3 is 24, right? And so since this is positive, since this is negative, we see that negative 5 is a max, and 3 is, since this is positive, we see that 3 is a min. Okay. So again, we get the same answer, but just by a different method. Okay. So you don't have to check the first derivative. You can check the second derivative. But really, once you got into the first derivative, you have all the information you need anyway. So, I like the first derivative test better than the second derivative test. Okay. So, any questions on how to use it? It's pretty straightforward, right? You take the first derivative and you look where the first derivatives are first derivative is 0. Okay. And then at those points, right, don't check other points. At those points where the first derivative is 0, check the sign of the second derivative, and if it's greater than 0, you get min. If it's less than 0, you get a max. So pretty simple. Okay, I'm going to stop there and hand back your exams. So on the whole, people did pretty well.